and welcome to this webinar that we're having as part of our electrification series. This is our fourth session in place, so we're happy for those that are back. If you're new and just joining us for the first time, welcome. We'll go over some housekeeping items in just a moment. Today's session, we're gonna, as mentioned in the title, really looking at battery design and thermal validation of electronic components. Today we'll be going through and building and analyzing a battery pack, and in this battery pack there's going to be a liquid coolant thermal management system, and we'll be starting off with a single cell and building it out from there. This will be followed by a thermal analysis of the system, where we'll be importing circuit data from an ECAD tool, and we're hoping this will be of interest to not just mechanical thermal engineers, but also PCB designers and others involved or wanting to learn more about these workflows. In terms of housekeeping items and who is involved in today's session, first and foremost, my name is Daniel Mazar, and I'll be your host for this webinar. As mentioned, I'm responsible for customer success and sales operations at Maya. I'm happy and engaged in where I'm able to leverage my electrical engineering background in supporting clients that Maya has across North America on complex engineering challenges and digitalization needs. Joining me is my colleague, Yafis Shakil Siddiqui. Yafis is one of our senior technical pre-sales engineers, and he has a vast amount of experience when it comes to, in particular, computational fluid dynamics, thermal management needs, but is able to scale and move beyond, and where he's able to solve a lot of different customer problems with his skill set, as well as his ability to gather information and bring others in. Both Yafis and I work at MyHGT, and I'll introduce mine in just one second. As I mentioned, this is our vehicle electrification series, where we've gone through a number of different sessions and subject matters for all of you. We started off where we looked more at electrical complexity and integrated electrical systems design. The next session, we looked more at demagnetization and being able to solve and analyze for EMAG-related issues and performance. The third session, the one we had last week, we looked at things from a different view, where we're now looking in a full vehicle context, being able to help do some component sizing, systems and subsystems integration and management. And finally, today's session, as I mentioned, is on battery design thermal validation. However, this last and final session that we've had in the series was based on audience input. So we appreciate for those of you that shared what you'd like to see next, what was of interest. So, you know, we definitely want this to be interactive and engaging. So again, this is based on your input, so we'll be hoping to have more of that interaction. With that, I'll jump into just some of the housekeeping items. As with our other webinars, this will be an interactive webinar, where throughout you will see short polling questions to help us better understand your reaction or response to the material that we present. It will also help us better cater to your specific needs as part of the material that will be presented. So we really do look forward to your input. However, this should not stop you from asking questions or engaging throughout. So if you do have a question or comment as we're moving through the material, please do ask your questions or share your comments in the features available in the GoToWebinar software, and we'll aim to address them at the end of the webinar. In case you run out of time or you think of questions later, we will connect with you afterwards by email, or you can feel free to reach us by email as well. Lastly, the presentation material will be shared afterwards, as it has been for the rest of the series. So we'll make available the recording as well as the slides that are being presented, so that you're able to go ahead and really get the most out of the material. As I mentioned, both Yafis and I work for Maya HGT. Just a quick introduction to our organization, so you know who's hosting this webinar and who's really bringing this for you. So Maya HGT is a leading provider of digital engineering solutions and the #1 global partner for Siemens digital industry software. Our history and heritage is in aerospace, always around developing and implementing engineering solutions. However, even though we started in aerospace, we've been working with many industries across the globe in solving these complex engineering challenges for the last 3 decades. In particular, there's been immense growth that we've seen around the engineering technology challenges related to vehicle electrification and it was that same interest and subject in relation to the subject matter that really brought this series to life. And so that's why we're happy to have you here if you're interested in learning a little bit more about that. Today, we're talking about battery design and thermal validation. However, when it comes to Maya, there's a lot more on the table in terms of what we're able to offer and do. So our expertise expands, starting from concept design all the way through manufacturing and then in-service analytics and real-time monitoring if and when needed. So this is just to share that there's a lot more in terms of the gears that are in place. We cover that small subset, but if you'd like to learn more about any of these areas, whether it's automating, customizing workflows, building specific wizards, or saying, okay, how can I stretch this out in relation to my organization's digitalization strategy or things we're looking to do in implementing machine learning algorithms, we're happy to engage in those conversations and bring the right people in. So with that, final note on the intro, I'm going to pass it off to Yafuz, and Yafuz is going to bring us through the technical content. Yafuz, please take us away.
Thank you very much, Dan. Dan, can you hear me clear?
Yes, I can.
Perfect, wonderful. So good afternoon, good morning, good evening for everyone attending today's session. As titled, the session is going to be on battery design and thermal validation of electronic components. So let me just jump into the agenda just to give you an idea of what you're expecting today. So essentially, I've divided this presentation into two sessions. The first one's going to be covering battery design, followed by that session on thermal validation of electronic systems. In battery design session, we'll be exploring an integrated workflow to analyze batteries all the way from its electrochemistry to full systems. We'll cover the challenges that battery designers face and how Siemens Solutions to resolve these challenges through its integrated workflow. So similarly, we'll explore the challenges faced by engineers who try to solve the same problem day in and day out. That is this electronic component within its allowable temperature? And if not, how do we make sure it is? In other words, ensuring the thermal validation of their electronic systems. We'll be covering the tools within the Siemens portfolio that covers all application and user profiles within the electronic supply chain. So without any further wait, let's just jump into battery design. But first, it's important to ask, why is battery design necessary? So the top reason that I think it is evident more than ever is because of the electrification of transportation. So every other day, there's news about another major car producer promising to switch to EV. This need is driven, in true honesty, due to the rise of Tesla and its vision for more environmentally friendly transportation methods. And hence, it's essentially been, pushing us to design batteries that are of higher power and higher density, higher efficiency, reliability, and safety. And this has led to designers needing to shorten manufacturing time. So we need fast analysis of many design variants in fewer time-consuming prototypes. Consequently, cost reduction is a need. We're talking about design costs, operational costs, and maintenance costs, to name a few. But most importantly, in all expanding industries, there is a need for innovation to remain competitive. And this means additional chemistry and reactions, wider operating ranges, novel processes and materials. So essentially, battery design is important, but what are the challenges you face when designing batteries? So let's jump into our first poll. Take it away, Dan.
Excellent. Thanks, Yafuz. Let me go ahead and share it. So again, we'd love to hear from you in terms of what is your biggest challenge when it comes to battery modeling. So you got 4 options in front of you that you should be seeing. First and foremost, setting up simulation is complex and time consuming. Second, multi-physics battery simulation is difficult to implement. Third, we depend on physical tests only. And fourth, we're not involved with batteries. So you may as well just be here in case you'd like to be involved in batteries in the future, or your organization is taking a look at it. So give you another 30 seconds. Would love to hear from you on what really is your biggest challenge right now. And again, if you're not directly involved with your org's battery modeling, that's fine. You could just give us your perspective of what you think the biggest challenge is. That'll help us as well. So we'll go ahead and just give it another 15 seconds or so. Okay. Excellent. I think we're ready to move on. So yeah, it was just to share some of the highlights and in terms of what we're seeing. So we did see answers all across the spectrum there. However, it seems the majority of people find that the setting up of the simulation is quite complex and time consuming. So that's really where the majority of respondents answered. There were a couple that said they felt that it was dependent mostly on physical testing, but really it seems to go back to complexity for those that are of interest here. With that, Yafis, I'll pass it back to you.
Perfect. Thank you, Dan. Well, that's exactly what I've seen currently in the industry. Essentially, there are no streamlined simulation tools available to address all the challenges of battery design, from cell microstructure all the way to full system simulations. We're referring to predicting and understanding the real world behavior of battery design from all the way from the start all the way to the end. There is no all-in-one solution set. And there are barely any solutions available for battery simulations, and those that are available are disconnected over the entire process. Another big challenge is the dependency on costly and time-consuming prototype-driven design and physical qualification tests for thermal validation of components. Now, we know that physical testing stifles the ability to explore many design variants in development and essentially becomes a barrier to innovation. Another common challenge is setting up the simulation for thermal validation of battery packs and electronic systems, which contain thousands of parts. It's time-consuming, difficult, and error-prone. Essentially, today we will look into the Siemens solution that streamlines the design of a battery virtually from cell microstructure to a single cell design to cells in the battery pack and batteries in full systems, while using simulation to reach your optimum design based on your objectives and constraints. Let's have a look at the engineering process for battery design and the Siemens solution offering. So the solutions available are capable to analyze a wide range of length scales, and this is perfectly appropriate as studying and designing batteries is a multi-scale problem. We're going to start small and move up from there. So our software portfolio can start all the way with studying the microstructure electrochemistry. The engineer here can study in 3D the effect of the electrode morphology on the electrochemical performance. Now, this tool is addressed to material manufacturers and cell designers. Then moving on to the cell level. Our solutions have the unique capability on the market to allow the cell designer to build a digital twin of the cell by configuring with high fidelity each component of the cell design. Now, this design can be coupled to performance models to test virtually the cell in various conditions like dry cycles, pulses, etc. Now, to study packs and modules, let's move to the next level. That is, build and analyze the complexity of the pack and its thermal management system. What's key over here is we're able to leverage our cell design in the previous step and build packs in a streamlined workflow with a few clicks. This process is generally tedious when setting up batteries with hundreds and thousands of cells. Here, we can analyze thermal behavior while understanding the highly coupled behavior of the pack's electrical performance and the surrounding environment. Now, finally, to the study of a full system. Co-simulation between system simulation tools introduced in the last session can bring even more realism in actual drive cycles applied to the pack. Essentially, we can bring a full breadth of solutions within the battery modeling solution process today. But for today's presentation, we're just going to focus on these 3 sections. That's the virtual cell design and test, the battery pack, and the system design. And the reason, because what we have seen and what I've seen with most of our customers, this is where their interest lies in. Generally, a lot of the customers would buy their cells from third-party suppliers. So before I jump into tool set, I would like to go through some success stories that Maya has had in the battery space. First and foremost, Line Electric Company. So Line Electric Company has worked with Maya to identify the best digital analysis tool for optimizing the battery design for their zero emissions school bus. In pursuing the goal of improving society, the environment, and the quality of life, this company based in Saint Jerome, Quebec, actually not too far away from the Maya offices uses modeling and simulation to create better designs and opportunities for innovation and forward-thinking vehicle design. So they were able to accurately evaluate safety, energy consumption, passenger comfort, and vehicle performance all through simulation, reducing costs and driving innovation. Another story that I like to touch upon is Kerberos. So they design outdoor recreational vehicles, and using the solutions that I will be presenting today, they designed a novel air coolant-based thermal system to optimize for electrothermal, stress, and aging. The video to the left is what you are able to see, what you're able to see in the variation of battery volumetric heat for a WLTC drive cycle for passively air-cooled pack. And on the right, you're seeing the temperature rise. There are many household names that Maya work with within the EV and battery industry. And Maya as a company has a lot of exposure in understanding the problems they face and providing quick and efficient solutions. So today I'm going to showcase a quick and simple example of how to build a battery pack from a single unit cell and then analyze the pack in a system level model. So essentially, we're going to start with the unit cell, leverage that data to build a 3D model, and then finally connect the 3D model to a 1D system to analyze the performance based on actual performance data, right? So let's just quickly go through a workflow overview. So in terms of, we're going to start the simulation from a single cell design, right? Build up the battery pack based on that information, set up the physics, and then post-process and analyze the results. But we're going to take it one step further and use this automated process to drive design change and finally design optimization, right? So let's just jump right into the first step, that is the single unit cell design. So before I jump into this, how is this different than what's currently been done? What is the current process of cell unit design? So when designing cells, traditionally the properties of the various chemical components are communicated on data sheets to battery manufacturers, who then create a cell that attempt to meet the criteria that are specified. Within the Siemens portfolio, we have a platform where we can combine the electrochemical properties of varied electrode and electrolyte materials and accurately model their performance against critical criteria. This essentially reduces the gap between laboratory and implementation considerably. So in this step, we're going to characterize the geometry, sizing, and materials of a single cell, and then test the performance of the cell thoroughly. We will also set the data for the load cycle to test in the cycle in 3D. So let's just jump right into the tool. Our solution allows the user essentially to create with great accuracy the digital twin of the cell. The geometrical details in all the components of the cells will be precisely defined. So we're going to create a lithium-ion battery. You can create a cylindrical and stacked configuration. In this session, we're going to be creating a lithium-ion stacked battery cell. In this solution, a default geometrical representation is created, which can be easily edited. Other than building the geometrical representation, we can set up the material properties as well, calculate the associated costing parameters for our design. Moreover, we can couple the geometry to performance models. Now, these performance models, they could be physics-based or equivalent circuit models. In this demo, we will simulate the cell performance under a discharge cycle. So the current rating of this given cell is around 10 ampere hours. And so we're going to set up a discharge cycle of 10 amperes in 1 hour and create a cyclic procedure. But using this tool, you can provide any condition pulses or duty cycle that you would like to run, right? Just another point to note out that the solution comes with an aging model to study the effect of calendar and cyclic aging by resolving the mechanism of the SEI, the solid electrolyte interface growth. Thermal abuse tests can be simulated, such as oven test or arc test. The model can be configured to predict the point at which the cell enters in thermal runaway. Talk about more about this later. What we just completed was create a physical representation of the cell design under a discharge cycle. So let's move on to the next step. So in the next step, what we'll be doing is taking the cell design and leveraging the geometry and material properties to develop a 3D model of our cell. Note that the solution that I presented earlier resolved the performance of the cell in a 1D representation based on physics or equivalent circuit models. Generally, as a user, if you had to do this process manually, you have to import the data into a 3D model. which is time-consuming and error-prone. So let's see how this is done in our toolset. The multi-physics tool that I'm presenting right now has a dedicated workflow for battery modeling for simulating the electrical and thermal response of a battery over the course of a load cycle. Activating this workflow is a matter of a few clicks. The added value of this workflow is that it leverages the single unit design we set up moments ago. We can use the design to not only analyze the single cell thermal and electrical response in 3D, but we can use it to generate a full battery module and analyze them. I'll come to this later in the demo. First, let's just model a single unit cell. The first steps of the battery module generation process is building the geometry and connector part. Here we are going to do this with the data of the single unit cell with no other user input required. As you can see here, the battery module has been imported in 3D with the material properties in place as well. Now we will set up the battery module. As mentioned earlier, we'll be creating a battery module with just one cell, and then we'll expand the simulation to connect 3 cells in series. Once the geometry generation is complete, we'll assign them to regions, and this is where we'll define the boundary conditions. Now this process is automated and is essentially done with one click. Now, the next step would essentially be setting up the circuit, that is connecting the battery to the discharge cycle that we had created previously. More than just simulating thermal loads, we can use the circuit solver that's inbuilt in this tool to connect battery modules with electrical loads as well. So we just imported that circular circuit module that we had created in our previous step, and now we're going to create circuit elements that is going to connect the battery to this cyclic profile, and that cyclic profile was the 10 ampere discharge over a period of 1 hour. So the final step, in this process would be essentially setting up the solver parameters before we mesh the domain. The meshing is usually the toughest part, but within the workflow, you can do this with just a few clicks. Now, before we complete the meshing, we need to jump into the solver settings and make sure we set up those correctly. We're going to set up a time step of 1 second just to resolve this much faster. But also we're going to set up the total runtime for 90 seconds instead of the 1 hour, just for time convenience. Finally, once the settings are complete, we're going to execute the meshing and observe the mesh quality. One thing to note about this tool is that not only is the solving process parallelized, but also the meshing process. And you can use up all your cores to do this sort of operation. So as you can see over here, the mesh is well defined, and now we can move into solving. So one thing to note as well is that the workflow for the battery setup is not only limited to pre-processing, but also post-processing. When you activate the battery module, the user interface is exposed to parameters that are relevant to battery designers. Here, we're going to visualize the battery volumetric heat on the front face in the scene. So more than just, as you can see, the fuel functions are automatically generated that is relevant to battery design, and they no longer need to be user-defined. What we'll also be doing is we'll be creating a plot of the battery voltage and measure that against time. One thing that's great about this tool is that essentially we can observe the solution in real time as the solution is iterating, and that's why we created the post-processing scenes prior to solving. So once we hit the run button, you're going to see the solution iterate, but also the post-processing scene update in real time, which is great, especially if you want to observe your results before it converges, or even it's good to catch in errors if you've made any mistakes in setting up the boundary conditions. So now let's go to the next step. We're essentially going to take the single cell and replicate this entire workflow, but to do it with 3 cells. If you were to do this in a general modeling process, you would need a lot of manual intervention. The user would essentially have to recreate the geometry, reset up the physics, mesh all the components and the boundary conditions for each of the test case. So let's just see how this process is automated in our solution. So now we'll be leveraging the same model we just created. Here we're going to extend the number of cells from 1 to 3 in the battery module. We will have to arrange the battery such that the terminals are aligned. Now we will generate all the parts. But first, we need to import the connector. Generally for connectors, they would have to be manually set up and put into place to where the battery parts are located. But within this workflow, all you need to do is import the connectors and attach it to the tabs through an inbuilt function. So once the connector is imported and the connections are made, we're going to go into generating the parts. So right now we've only generated the part of the first module. We're going to continue the process by generating the parts of all the cells. As you can see here, the cells have been imported with the connectors set up in series. In this model, we'll also imprint all the parts, and this is essentially to ensure all the parts are connected and the contacts are generated. So once that's done, we're going to apply new cells to regions to set up the boundary condition. Again, this process is completely automated and can be done in a few clicks. And similar to the entire process of setting up, even the meshing process is again as simple as right-click onto the battery module and generating the required mesh. So essentially, while the model is meshing, I'd like to highlight that the electrical connections do not need to be redefined. The rest of the material properties are already in place. If you were essentially to do this manually, it would be too tedious, time-consuming, and error-prone. So you can also add any external casing if required, and that is built in within this workflow. So essentially, all that we need to do once the meshing process is complete is declare the solution and rerun it. One important thing to note is that we're going to reuse the same post-processing scenes we generated earlier. And essentially, this completes the simulation of a cell in series. Let's move on to the next part of the demo, and that is the design exploration or optimization. Now, design exploration is typically the holy grail of simulation. Validating a design is generally the stepping stone. And at the end of the day, getting a better design quickly is typically what people are gunning for when investing in simulation. And this is what I'll be showcasing now. Now, before I jump into design exploration, what's important to have is an automated workflow. And so the first thing to an automated workflow is being able to rapidly iterate designs. And the first step to that is having a model that is parameterizable. Here, the thermal management system of a battery pack has been imported from a CAD tool alongside its parameters. Now, the parameters can be updated with a single click of a button, and all you need to do is execute this automated workflow and run the solution. In this setup, we're quickly going to change the dimensions of the cooling system, remesh, and then compare the earlier design to the new design. The idea is that we want to be able to take the parameters that are fed into this tool and drive an optimization study. What's great about this tool is that it has an inbuilt optimizer, and no scripts are required to set up this optimization study, and all these parameters are directly exposed and requires no manual intervention. So here, as I said, we're going to be comparing the two designs and then be able to feed those parameters into the design exploration study. So I'm just going to visualize the results, and as I mentioned before, the results can be seen live without the need to wait for the solution to converge. And that's exactly what you're seeing here. As the solution is iterating, we're looking at the solution update. Now, let's just take it to the next level. That is the design exploration study. Let's take a common objective that all battery designers look for, that is minimizing the pack weight. And another objective would be to minimize the coolant channel's pressure drop to reduce energy consumption by the cooling system. In terms of constraints, we're going to ensure that the maximum temperature is less than 60 degrees, and you definitely need a low temperature gradient to avoid structural stresses and hence we're looking for a max temperature difference of less than 3 degrees across the entire design. So let's just jump into what the optimization solver did. And so over here, like I mentioned, we're looking at a Pareto plot of pressure drop versus decreased weight. And what key thing about this optimization, as I mentioned, is it's all automated. It is complete. It's searching the design space through a state-of-the-art Sherpa algorithm. And on the screen, what you're seeing are dots, and each dot is a different design. A blue dot is a feasible design. A red dot is a design that has not met the requirements. So essentially, this simulation was run over 3 days with 120 CPU cores, and was able to find a much lighter design with a much lower energy requirement. And this is what we're gunning with simulation. Now, the examples that I've shown right now are somewhat simple in terms of thermal flow simulations with electrical circuits. Now, they're relatively simple, but there is one issue that battery designers are very concerned about, and that is thermal runaway, and that is a much complex simulation. So thermal runaway is essentially a situation where the current flowing through the cell or battery on charge or overcharge causes the cell temperature to rise, which increases the current with a further rise in temperature. This often leads to explosions. And when you hear about exploding batteries, this is the phenomenon that occurs. And this is something we all hear about and are all concerned about. So modeling thermal runaway requires more than thermal and flow and electrical. It also requires understanding of combustion, gas expansion, and many other phenomena. So within our tool set, we have the capability of modeling such complex phenomena. So on the left-hand side, you're looking at examples of thermal runaway simulations conducted through our multi-physics CFD analysis. Now, through our solution, we can go beyond that. We also have the capability of looking at acoustics, fluid structure interaction, which would be key in this example, but also corrosion, electrochemistry, electromagnetics, to name a few. So jumping back into the demo, we analyze the battery as an individual component at a given current cycle and with a steady load. Now, these conditions were based on a given profile. But in real life situations, the profiles are constantly changing. The batteries are part of a complex system. They're multi-domain containing of electrical systems, control systems, hydraulics, to name a few. Now, the challenge is, how do we virtually verify a complete system and not just components? Now, this could be accomplished by multi-physics system simulation. Now, for those who attended the last session are well aware of what SimCenter Amazon is and what it is capable of. So it is an integrated, scalable system simulation platform which allows you to do multi-physics simulation combining electrical, thermal, hydraulics, mechanical, and controls to virtually assess and optimize an entire mechatronic system's performance. The tools can also connect to more detailed analysis solutions like 3D CFD for detailed fluid modeling or finite element analysis for structural analysis. And this is what I'm going to showcase right now and see how this works in practice. Now, in this example, we'll be modeling the thermal management system of an electric battery pack and validate the performance while a vehicle is moving. So essentially, the input here is the velocity of the vehicle, which will determine the cooling performance of the radiator. Cold coolant from the radiator is fed into the battery pack, and the hot coolant from the outlet of the battery is fed back into the radiator to be cooled. Amazon will represent the entire cooling system. It will provide the temperature and mass flow boundary conditions at the inlet of the battery pack. Whereas our 3D CFD solution will calculate the heat flux from the pack into the coolant and provide the coolant outlet pressure and temperature to Amazon. So let's jump into the model. So this is the Amazon model. As you can see, there's a TCP port that will be our connection to the CFD tool. It's as simple as setting up a port and having the inputs and outputs connected to the radiator here. So this is our CFD tool. We are leveraging the same battery workflow to set up the simulation. The mass flow input is going to be a variable that is fed by Amazon, and the pressure outlet is going to be an output that is fed into Amazon to complete the circuit. Now, to set up that connection in the CFD tool, it's quite simple. It's nothing but activating the Amazon workflow and setting up the correct port number. Just a moment. All right, so we're just looking at the boundary conditions out here, just making sure that these are the ones associated. And like I mentioned earlier, the connection to the CFD tool is nothing but just activating that workflow. As you can see, we're here in center image and explicit coupling. Now, all that is now left is to verify that the settings in the connection link is the same as that of the CFD tool and AMSIM. Now, based on my experience and what we've seen, is a lot of companies do not perform this, and those who do perform these sort of simulations, they always require in-house scripts. Now, these scripts are usually valid for a given release, and they need to be constantly updated. Now, we were able to achieve the sort of connection through built-in capabilities with no need for user scripts. All we need to do is hit the run button, and the solution will now update as we go through time. So every time step, as the solution updates within the CFD model, it's going to export those results into AMSIM to move to the next time step. So let's just wait for one time step to move, and we're going to see the data transfer from one tool to the other. So as the solution is updated over here, we run to the AMSIM model, and you can see the solution is stepping forward in time. So let me just jump into the results. So here are the 3D CFD results on the left-hand side from our CFD tool, and to the right are the 1D results looking at the temperature of the inlet and the coolant mass flow rate based on an actual life cycle. Well, now there's going to be a pop quiz, and the winner gets, actually there's no pop quiz, I'm just kidding. We're just going to, sorry for those who got excited, we're just going to jump into another poll where, we're going to see, where do you see the most value presented in the battery workflow? Dan, go ahead.
Thanks, Yafez. It's funny because you mentioned pop quiz and the audience attention level goes up. I think we've all been hardwired since school for that. So you should be seeing the next poll, as Yafez mentioned. Again, it's not about right or wrong. It's just about learning what's of interest to you. So where do you see the most value in the presented battery workflow? A, ability to leverage the data from design stages. B, advanced multi-physics capabilities bringing realism. C, ease of use to set up the simulation. Or D, we don't see any value in battery simulation. Again, no wrong answers here. We're just trying to make sure we're continuing to cater the presentation, or if, let's say, it's beyond the bounds of what we're aiming to cover, then that'll at least give us a good data point on how to adjust for future presentations. So again, if you could please just take another 10 seconds or so and just give us your best guess. Again, it's not about being right or wrong. We just like to hear your opinion over here. Great. Seeing a decent number of questions or answers coming in. With that, I'm going to go ahead and close the poll. So Yafez, no, there wasn't a single person who said that they didn't see any value in battery sim, which I think is relevant to the audience that we have on hand. The majority of people felt that really it was the advanced multi-physics capabilities. That's where they see a lot of value. And beyond that, it was also option A, which was around being able to leverage the data from the design stage onwards. I think based on what they've seen, very few people actually found the ease of use part to be of interest yet. So, maybe you'd like to touch on that as we move forward with the presentation. But right now, really, it is the enhanced capabilities where the interest is coming in. So good data points. Appreciate everyone filling it out. And with that, I'm going to pass to Yafez to bring us forward.
Perfect. Thank you, Dan. So essentially just, doing a quick recap, we have the entire breadth of capabilities available for battery design. For those who are not in battery design, we're moving into a world where electrification is the future, and hence battery design will be something that as engineers will be always considering. So this is good to know in case it does come onto your table one day, and you know who to reach out. So this sort of marks the end of the first section of the presentation today. Now the second section is going to explore the thermal validation of electronic components. So let's touch a bit upon why That's important. Now, the biggest single reason that electronics fail is excessive heat. Now, over half of all electronics failure can be traced to thermal issues. Failing to understand product performance during development, if not caught, can essentially lead to field failures, which in an extreme case can lead to billions of dollars in lost revenue. Everything's heard about, the Samsung fiasco, what happened with the Galaxy Note 9, and essentially, it's an untold damage to the product brand and the company's reputation as well. But there are other challenges that are faced as well. So across all markets, miniaturization is a trend. Companies are also trying to be the first to market a better performing product that is more innovative than the competition. There's a need to reduce costs, and these are costs associated with product development as well, and to maintain and achieve the same or better margins as competitors. And moreover, companies often have bottlenecks associated with the performance of the product during its development. And rework if design changes have inadvertently degraded some of its performance, for example, its thermal performance. So from an engineering perspective, many questions can be asked in order to push the boundaries of what is feasible. So one thing that's constantly asked is my current solution keeping all the components under the critical temperature points during severe operating conditions? How much does a large change in the air cooler decrease the cooling performance? So from a point of view of creating, a digital twin, starting with a digital twin, you can capture the thermal performance of the product and be the most effective to improve product performance, which is quite evident. However, we all know with simulation comes a set of challenges. But first, I'm just going to run into another poll and try to understand what is your biggest challenge in electronic thermal design. Hey Dan, could you
Great.
run the next poll? Go ahead.
Yes, sorry, I was on mute. Excellent.
No.
So as Yafis is addressing again, in talking about electronic thermal simulation, we're trying to understand what your biggest challenge is over here. So we have 4 options. A, there's no streamlined workflow to use from the ECAD systems. B, electronic simulation itself is complex and time consuming. C, we depend on physical testing only. Or D, we're not involved with designing electronics. So again, love to hear if just these areas, even if you don't, your best guess is also appreciated in helping us gauge your interest level as well as where you think it's relevant for your organization. All right, let's see what's going on. All right, thanks for those that were able to fill it out. I think we're ready to move forward here. So just in terms of answers that we're seeing, Yafis, everyone's involved with designing electronics, so that part's good. The majority of people, in terms of their biggest challenge, I'd say about half the respondents shared that it's the fact that electronic simulation is complex and time consuming. There is a small subsegment of the audience that is mostly focused on physical testing for this portion. However, there's another area that says that there's no streamlined focus. So again, everyone's involved with designing electronics. Majority find that it's too complex and time consuming. And there's more or less an even split between those who do physical testing as well as those that are having issues with the workflow itself. So that should give you a good indicator for the next segment. I'll pass it back to you.
Perfect. Thank you, Dan. So again, this is exactly the same challenges that are faced by most of our electronic thermal simulation customers. So one thing that we've learned from just the battery simulation as well is that simulation is a workflow, and along with that workflow are obstacles. So let's just think about it from a user level. From a user level, we can think about doing multiple design iterations, which requires multiple and repetitive tasks. So how do we achieve modeled realism to give accurate results is also another challenge. There's also a lack of best practices available for accomplishing accurate simulation. But now let's just look at some of the challenges that could be faced on an enterprise level. how can we connect and integrate existing softwares together to set up processes, and how can we efficiently collaborate, share, and reuse simulation data and models. So these are just some of the challenges to achieving the true value of CAE, which is design validation and exploration. Now, with the Holy Grail being implemented, an automated workflow to create better designs faster is what we're looking for. So in the next part of this session, we're going to address these challenges when modeling electronic systems. We're going to address how the tools within the Siemens portfolio can leverage your electronic system data to perform thermal analysis of integrated circuits, then all the way down to chips or even die level, and then all the way to full electronic systems. Let's just look at the electronic supply chain and the packaging level for essentially, conventional electronics. So thermal design is performed, it's performed from the integrated circuit chip or die level all the way to data centers. Now, let's just go through the supply chain. A silicon chip gets into a data center through many companies that design and manufacture first the chip, who then package it into a component. You could have manufacturers for the printed circuit board that solder the components to it. Then there are people who assemble the boards into modules to create, for example, power supply or disk drive unit or a switch for a data center rack. Then you integrate these modules into systems, so switches, servers, and storage units that might be integrated together into a rack. You integrate those systems together into platforms or systems of systems, such as a full room full of racks for a data center, or integrate an infotainment system into a car. So if you do look at any electronic device, know that it is not one single manufacturer, but the multiple manufacturers, and this makes the entire process very complicated. Different companies, design and manufacture these different parts, and each making assumptions about how these are cooled, and then designing them in anticipation of that. So for example, a CPU for your computer may be designed so that heat can be removed most easily through a heat sink that should be attached to the top of the package. Now, thermal design of the final product should be optimized also for cost, weight, and volume, but clearly multiple members of the supply chain do not have control over that. So a holistic design approach to thermal design is very desirable. So starting from the ideation phase of these electronic systems, it's generally managed by thermal specialists and designers. However, as we go into subsystems to system level, that is into the electronic supply chain, these electronic systems are implemented into mechanical devices, such as an IGBT in an electric motor, controls for battery systems, so on and so forth. So mechanical engineers are more involved in the design process. So within the Siemens portfolio, we have solutions that meet the entire breadth of users and applications. So first, let's look at a quick glance at the users of these electronic solutions and what is available. So as mentioned before, we have a dedicated simulation tool for electronics cooling within Siemens PLM, which address various user personas and applications, and these solutions are complementary to one another. So starting with thermal specialists and designers, as shown, these solutions are aimed to resolve electronic cooling challenges from die level all the way to data centers. But we also offer engineers the most comprehensive multi-physics CFD capabilities available, capable of addressing all fluid physics challenges. Now, these two solutions are complemented by CFD solutions that are embedded in major mechanical CAD systems, front-loading simulation in the development process by making CFD accessible to engineering designers. In summary, we offer the broadest range of CFD solutions for the electronics and semiconductor industries. So with all these available solutions, where can we apply them? Here is a quick snapshot of some of the few applications our customers are using our electronic system cooling solution. So beyond board level and system level simulations, we're looking at spray cooling of electric motors, LED lights, thermal performance. It could be convection, cooling due to liquid cooled plate for power electronics, but also generally by forced convection, and that's what we're more used to. So now let's go back to the supply chain of electronics. So for the next demo, I'm just going to jump into the solutions first used by the thermal engineer specialist, and then we'll jump into mechanical engineer. So let's start with solutions for PreCAD analysis. So what does that mean? Solutions for thermal engineers need to be easy to use from a CAD perspective. They are not CAD users. This Siemens solution has built-in library of parts to quickly validate concepts and designs, such as fans, boards, heat sinks, etc. But moreover, it has a large library of components from chip manufacturers and board suppliers that the user can bring in with a click of a button. Here we're going to do a quick analysis of a PCB board with a chip. We can also easily add in heat sinks from the smart part library. One key feature of this tool is its meshing capability. It requires little to no user intervention. That, along with a robust solver, this tool is designed to be used by non-CFD experts, and these are thermal specialists and designers. So we're going to quickly run the simulation and just analyze the results through a simple method. As I said, it has a very robust solver, and this solution was completed in 6 seconds on a big desktop. Here we're not only analyzing the temperatures on the board, but also the fluid temperatures. Now moving up to the electronic supply chain. The next solution presented is more CAD-centric. It can still, however, leverage the smart parts and components library. The simulation can be easily set up through a wizard-like workflow. No expert CFD knowledge is required. As you can see here, the user is just setting up an analysis through a wizard, and setting up the material properties through the extensive library produced. But moreover, you can import ECAD files and convert them into CAD data, taking in the detailed component and simplifying them on the level of complexity of your choosing. If you'd like, you can model all the layers of the PCB in full detail if needed. The meshing process is fast and again does not require much user input. Another key benefit, of this solution is being able to parameterize the geometry and boundary conditions. And we're just going to show that here quickly. What we're going to achieve to do is parameterize one of the components and then run a parametric study. As mentioned before, the meshing process is fast and again does not require much user input in separating the mesh for the solid or the fluid. It has a meshing capability called Smart Cell technology. Now going back here, we're going to run a parametric study, and in this case, we're going to adjust the number of fans in this given design. We're going to analyze 3 sets of data, looking at reducing the temperature of the components. What's key about this solution is that everything is inbuilt within the same user interface. You don't need to export the data to another tool to analyze the results and compare them. Now, going back to the supply chain, what we saw was just the thermal specialists and designers, but what about the mechanical designers? I'm just going to go and show a quick snapshot of the capabilities available. As mentioned earlier, we have high-end multi-physics simulation to do, very strong optimization studies, and also to do electronic cooling systems, such as the e-cooling motor in a more, very efficient manner. But then we also have CAD embedded solutions for designers so that they can front-load simulation early on in the design process in reducing engineering time. Now, all that I have shown are in terms of the breadth of the solutions are for thermal analysis. But whenever we're talking about electronics, it's very important to address the electromechanical design. Now, Siemens has developed tools to ensure electromechanical integration, and this integration I'll just divide into 2 levels. The first level is the harness level with the IES Portfolio tools that was covered in the first session of the Electrification series. And the second is the PCB physical layout level covered by Expedition, PCB Exchange, and a new kid on the block, Alma. So this slide shows the highest level integration between these tools between electrical, electronic, and MCAD. But what problems are we trying to solve? Now, ECAD and MCAD are 2 sets of tools with very different capabilities. Design iterations between ECAD and MCAD are difficult, manual, and error-prone. Data synchronization is often an issue. Design issues between ECAD and MCAD often cause redesign and sometimes major issues in the final product. Manufacturers now seek a high degree of integration between their businesses and design tools. MCAD, ECAD, and PLM systems are no longer selected purely through their individual functionalities. They must also integrate. and the integration must include all the data in the processes. So what are the benefits? It promotes design review collaboration through visualization and sharing of engineering information. It helps eliminate synchronicity errors between ECAD and MCAD design. And the gateway between mechanical and electrical has traditionally been challenging. 50% of complex products require at least one additional design iteration to address electromechanical issues. And 68% of corporations cite ECAD MCAD design synchronization as a significant product design challenge. Through the Siemens portfolio, we're not only connecting the entire supply chain from one user to another in terms of thermal application, but also connecting the electrical and electronic systems. But I also like to touch upon Alma, and this is a feature developed by Maya, which promotes design review collaboration through visualization and sharing of engineering information. So Alma, what is it? It's a standalone lightweight visualization tool for schematic PCB layout and 3D CAD with full cross probing and markup. It's an ECAD agnostic application. It validates ECAD and MCAD data synchronization. It reduces errors before manufacturers access design data without the design tools. So looking at the video out here, Alma can be used to cross-select and compare with electronic design, supporting an integrated workflow across the design domains. It's used to load the schematic and PCB layout data, while CAD takes care of the 3D data. So a Mentor Expedition user can use Alma to cross-select and compare with mechanical design. A CAD file generator can be loaded into Alma while the user is working on the electric design. So essentially, this marks the end of the second session covering thermal validation and electronic systems. I touched upon a bit on the connection to electrical and electronics. But before we move into concluding remarks, I'd like to run a poll. So Dan, could we go on to the fourth poll?
Yep, I am on it. Bear with me. Great. And there we go. So it should be showing up shortly right now. So again, on the system side, as Yafas is going over, sharing a little bit about Alma, we wanted to get into understanding the value around the electronic system simulation piece. So 4 options here for you in terms of where do you see the biggest value that is being presented in the electronic system simulation solution. A, solutions cater towards every user group. B, the ability to leverage data from the various design stages. C, ease of use to set up simulation for non-experts. Or D, we don't see any value in the current workflow. As with the previous ones, again, there's a good number of options here. Yafas, while we wait for the responses to come in, based on what you're seeing in the industry, where do you find the biggest value being shared by clients and users?
I think the biggest value that we see is definitely that the solutions cater to every user group. Each electronic supplier or manufacturer, based on where they are in the supply chain, are looking for a tool that's more specialized towards them. And these tools that we provide within the Siemens portfolio, they might seem broad, but the idea is that we are able to cater to every solution requirement from the customer.
Oh, that's a great point. I think we're seeing a little bit of that in the responses as well. I'm going to go ahead and close the poll and share in a second. But funny enough, the largest majority of respondents did feel that it went back to just the ease of use to set up a simulation for non-experts. I think there is some relation to option A there in terms of how the solution caters to every user group, which did have a certain number of respondents. But there's a huge chunk of attendees that also felt that the ability to leverage the data from the different departments has quite a bit of value. Interestingly, everybody does see some value, so options A through C. But again, the majority went back towards the ease of use side of things. So good to see it does relate. And again, for you, it went back towards what you're seeing in terms of catering to every user group. So ease of use, the catering piece, and the data transfer, all of relevance here for our attendees. With that, Yafas, I'll pass it back to you.
That's perfect, Dan. Yeah, Dan, I think I might have to reiterate on that. I think it's easy for me to find a solution for a customer, and so it's not a challenge for me to cater to the solutions of the customers. They might find it ease of use, which of course is very key. So going back to looking at the electronic supply chain, we've got all the solutions for all breadth of user levels and all different types of levels within that supply chain. And so, essentially, whatever need you have within a given design workflow, I'd like to run another poll just to give an understanding of your design process. Now, this could be irrelevant to either battery design or electronic cooling systems, but let's just run this poll to understand where you stand in this workflow.
Great. Yeah, so are you able to see the poll?
Yes, I can see the poll.
Okay, great. So again, this one just goes back to your specific engineering design workflow. Love to hear about it. So are you satisfied with your current workflow? Yes, we have an efficient, streamlined process. No, we could benefit from using sim. Or C, no, we use simulation, but the workflow as is has its bottlenecks. Again, just give a few seconds. Again, no grading or quizzing here. So just keep us posted on it. All right. I'm looking to wrap this up again in just a few seconds. But yeah, if it's majority of audience is saying that no, they could benefit from the simulation side of things. There's a small handful that are saying that on both options A and C, where there's a few that do believe that they have an efficient and streamlined design process, whereas there's also a few that says they use sim, but there's some bottlenecks there. So again, majority saying we could benefit, but we are seeing across the spectrum answers coming in. So with that, I'll pass it back to you.
Perfect, Dan. So Dan, before we end the presentation, I want to focus on this slide, and that is going beyond electrification series. Do you want to put in some concluding remarks before we talk about next steps?
Absolutely, and I really appreciate that work that you put in there, Yafis. And again, relating back to that last poll, but we're in this series, we're trying to teach and really focus on the entire engineering workflow, showing you how can we go ahead and help you streamline and improve things with validated industry-specific workflows. So that's what we were aiming to do in putting this series together. So, in-house, we do have a multidisciplinary team that has vast experience in resolving technical challenges and bringing in those efficiency and proficiency gains. So there's a lot of pieces that we're able to bring in. One of the key ones that we'll share, and that will be on the next slide as well, is we strongly recommend checking out our simulation assessment. We're making it complimentary for any of the attendees of the series as a thank you, because we believe you've kind of dedicated your time, which in itself is like money. So we'll walk you through in terms of understanding your current design workflows, what are some of the challenges that we're seeing, and then share with you some of the industry best case practices we have. We did this recently with a customer where, in trying to understand their business objectives, we're able to help them remap their design process to reduce it from 18 months to 12 months and help position them for further growth in their market. So definitely something I recommend you check out. Do send us a note if you're interested. Yeah, if there's anything else you want to add on this slide before I wrap up?
No, that's it.
Perfect. So I think that's a good segue into this last slide here, which gets us into our what's next piece. So for those that have attended and checked out the series, we've talked about a lot of different tools and workflows. We really wanted to cater throughout the vehicle electrification spectrum in terms of different engineering needs. So we're actually putting together a software package for any of the users that have been attending that would like to check this out. This will have pieces related to the different softwares that you've seen throughout. Maybe only certain ones, for example, you said, hey, I'd rather just focus on the systems piece, or I just want to talk about, simulating on thermal components. So we can, it's modular, and it's at no added cost for you. So if you're interested in checking out this package or having access to these tools, please don't hesitate to get in touch. This is an invite-only series, so you can email your account manager and say, hey, I'd like to learn more about the software package or talk about, the tools that are included. If you don't have one and you still like that info, please email us at info@myhtt.com. We're making this available for any of the attendees up until the end of Jan 2021. So you have until then to let us know you're interested, and we'll be able to share that complimentary package with you. Beyond that, I talked about the workflow assessment. So there's definitely a lot of efficiency gains there. And as a thank you for attending and joining us, that's going to be a part of it as well. If you'd like to just learn more about it, schedule a 30-minute session. Again, that's going to be part of our complimentary access for attendees. And lastly, in terms of additional web series, so this is the conclusion of the Electrification series. We do have multiple series that are starting in the new year. So we'll be talking about workflows from CAD to CAM, so on manufacturing. We'll have a deeper dive on thermal electronics and components. As well, we're going to have an additional discussion on simulation for designers. So do keep all those in mind and let us know if you're of interest. And in terms of just some final questions, again, thank you all for taking the time. There are two that I'll go through in relation to this webinar, and then just do a final wrap up on the series. So if you've missed the last webinar, or you'd like to see any of the webinars again, we've made them available and we'll continue doing so. You'll see a folder link sent out to you that'll have access and information on all of the different videos and sessions. So that'll be sent out to you later this week. In addition, Yafis, in going back to some of the audience questions, just want to make sure that we've gone ahead and looked at this. People wanted to know, just in terms of being able to validate some of these solutions with their current engineering design team, what would be the right next step to be able to look into that? Can you maybe share or shed some information there for us?
That's true. All right. So in terms of the next design step, I think it's exactly what you just talked about. Getting in touch with us, and we can provide you the best solutions available based on your requirements. So those are essentially the next steps. But other than that, based on whatever solution you thought was possible, we would essentially provide a guided evaluation into validating what the best design solution fits their needs.
Oh, excellent. I had one more question in terms of where to find more information. Again, we'll be sharing that in our follow-up presentation. Somebody asked what was one of the series I mentioned. I was talking about CAD, so we're going from design to manufacturing, so CAD to CAM series that will be launched early next year. So that's going to go through the whole design for manufacturing workflow, and we'll have multiple examples related to different industries around that. So that would be that series coming up as well. In addition, if you have more questions on the series that we had shared, as well as any of the material in relation to the presentation material we've had over the last couple of weeks, again, we'll make all of that available by the end of this week. You should have an email with it, so don't hesitate to let us know if you have more questions on it. Great. Last, definitely not least, did get a note saying, just wanted to do a quick thank you to all of our presenters. We've had a lot of subject matter experts come in. Yapa's fantastic job today. Thanks to all of you that have come in and share some of this information and questions and been with us throughout these series. We will have quite a few different topics coming up. I just see another note here with someone saying, could we do something on acoustics? Answer there would be yes. I'm not sure of what context. So we may reach out just to see if there was a specific topic or area of interest. It may be part of a series, maybe a separate series, or it may just be a conversation with you. So we can circle back on that one. But if you have more topics, more ideas that you're interested in, do let us know. If we're talking about multi-physics type simulation, absolutely, that's one of the main areas of interest and conversation that we see coming in. So please keep your eyes out for this kind of information. We will circle back with you by the end of this week. Once again, just wanted to thank all of you in being available and here with us. As I mentioned, we'll send this information to you. We'll make available the complimentary package as well as the workflow assessment. And we'll share details about upcoming webinars in the coming weeks there. So in the next couple of days, you should be having quite a bit of information from us. So thank you all once again for your time. Wishing you a great end of the year and your workday, and we look forward to talking to you in the near future. With that, we'll wrap up this webinar in the series. All right. Bye, everyone.